Welcome you all to our ICPS conferences. Everybody ready for Days of Science from Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. It's time to share your great knowledge of this science. Is everybody excited for this conference hosted by Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS. Welcome you all to our ICPS conferences. Everybody ready for Days of Science from Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. It's time to share your great knowledge of this science. Is everybody excited for this conference hosted by Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS.
Treasurer of the International Conference of Physics Students Puebla 2022. It's a great pleasure for me to introduce our next guest speaker, who is going to give us a talk about plasmonic response of nanoparticles arrays and its potential applications. Dr. Cecilia is member of the American Academy of Sciences and the National System of Researchers. Dr. Noguez is the current director of the Institute of Physics of UNAM. She is a leader in computational physics, recognized for her contribution in the fields of plasmonics, optical activity, and surface physics. She pioneered the study of plasmonic nanoparticles, which allowed establishing new concepts and lines of research. She is the co-author of numerous publications in specialized journals, which have been widely accepted by the scientific community. She has given more than 2,000 invited lectures at congresses, universities, and research centers in Europe and United States, Canada, Latin America, Australia, China, and Mexico. She has received numerous awards. Among the most recent are the 2016 National Science Award for her contribution to the country's scientific heritage and the honoris causa doctorate from the Autonomous University of Edo de Mexico in 2018. Without further ado, please join me in welcoming Dr. Cecilia Noguez. Welcome. It's a pleasure for us to have you.
Thank you very much. Thank you for the introduction. And well, I just want to say that I have just given around 200, 200 invited talks, not 2,000, but
sorry.
No, it's okay. That's too much, probably. Okay, well, I will share my screen with you. with my presentation, and as they said, I will talk to you about plasmonics, plasmonic arrays, and which is a potential application of this kind of system. As in the introduction, they say, well, I'm a part of the Physics Institute, where I am a researcher. I'm in Mexico City, and this is just a small view, the view of one of our buildings there. We have about 176 faculties in the institute. We have around 40 postdocs, 300 students, and other kind of staff, like 140 people. We have 51 laboratories in 70 spaces. We run 4 national laboratories, and we have more than 22,000 square meters in 7 buildings. Okay, and also we host about different classes at the Physics Institute, and we have another 300 students that are around normal conditions in the Physics Institute. So, well, after this small introduction of what is the Physics Institute, you can go to the webpage and to see what we do there. Let me just start. Okay. Let me see why it's not going to the next. Okay, now it's here. Well, what is plasmonics? Well, you can think that you have a system that has about n times e charges, positive charges, okay? And you have the same amount, okay, of negative charges. So let's consider a system where you don't have any, which is neutral and electrically neutral, but you have a system where the electrons can move a little bit free in some sense. Okay, so now let's consider that this system is under the action of an external field, electromagnetic field, okay? And when you have an electromagnetic field which is oscillating with some frequency, like this one, and is along one direction, for example, the x axis, whatever that means. What happened is that there is a force that move the negative charges, which are lighter, less massive than the positive one, which are the ions of the system. And they can move from the positive ones. And at the end, you can think that you have a surface charge distribution on the system, okay? So you have a force, which is the external force that is on these charges, okay, due to this electric field. And also you have an internal force between the positive and negative charges, okay, that is a Coulomb force, and they try to restore the position, let's say, of the electrons as compared with the ions. Now you have two forces which are competing. You have a total force in the system. You have these two forces which are competing, and when those forces are equal, you will have what we call a resonant mode. Okay, that means that all the electron cloud of the system, okay, so all the negative charges that we call the electron cloud, is moving with the same frequency, okay, as the external electromagnetic field, okay. And now we have a resonant frequency at a given frequency that we call omega 0, and all the electrons oscillate in that direction. This kind of this surface charge distribution give rise to an evanescent electromagnetic field, and that means that when you are close to the boundary of the particle, in this case, you have a electromagnetic field which has a large amplitude, and when you go far apart from this, the electromagnetic field goes to zero. That means that you have not a propagating modes. You have what we call a near field, not a far field. And this kind of system, these plasmonic systems that has these resonances, are characterized by this near field electromagnetic response for the particle. Okay. Now, what we have to do to understand what is going on with this particle, well, we have to solve the Maxwell equations, okay? And we have to solve the Maxwell equations on matter, in the presence of matter. And also we have to take into account this surface mode and this surface charge distribution, which is given in terms of the polarization field, okay? And one important thing that we have to consider is the dielectric response, or the dielectric function of the nanoparticle, as well as the dielectric function of the host where the particle or one particle or the particles are in the system. So also we have to take into account that these surface modes within the particle, this polarization field is equal to zero, the gradient and the rotational fields are equal to zero, and on the surface we have this surface charge distribution, okay? And this is given by this equation. Now, what happened? You can see here that you have some kind of array of the ions and the electrons as compared with these ions. So we have a distribution, a particular distribution of the charges on the surface. And for this particle, which is spherical in this case, this example, we have a very, let's say, smooth and simple form that the particles are distributed. However, when you have another kind of particles, like let's say cubic particles or whatever, this distribution is not as easy. And because you have, again, you have to think that you have the external force and the Coulomb force between particles, okay? And now each, this force, that give rise to this resonant mode, will have different kind of distribution of charges. I will show you later. And each nanoparticle will have different number of surface plasmon resonances that we have called in that way. And that depends on the nanoparticle shapes, okay? And the frequencies are determined by the material which is made the nanoparticle. For example, how many electrons are in the system, the electron density in a given volume. It also depends of the electron effective mass of the electrons. Okay, this effective mass is given by, for example, how the atoms are arrayed in this particle. Okay, it's not the same to have an FCC array or a phase cubic center array or just a simple cubic array or whatever. And so the mass of the electron is different in that sense. It also depends on the nanoparticle size, the dielectric environment where the particle is, and also with it is modified, the response to the electromagnetic field is modified by the presence of other polarizable bodies. That means the presence, for example, of another nanoparticle, an array of nanoparticles, or the presence of a substrate or something like that. Okay, if you have some question, you can let me, no, okay. Now, okay. As I said, well, the number of resonances and the frequency of the resonances will depend on the shape of the nanoparticle. For example, in this case, we can start with a sphere, okay? We can have, for a sphere, we have only one resonance. That depends, as I showed you, it's very homogeneous how the charges are distributed around the sphere. So you have a single resonance for the sphere, this one that I'm showing here, okay, and this purple line. However, for example, if you have a cubic nanoparticle, we have, for example, this dark line, the black line, actually, that has 1, 2, 3, 4, and we can see up to 6 different resonances because now we have a different kind of charge distribution on it. When we, for example, truncate the nanoparticle, which are very common synthesized in an experiment, for example, I am showing here a micrography of this kind of nanoparticle, and we can truncate the nanoparticle. These resonances will change just because of this arrangement of the charges in the surface of the nanoparticle. Okay, so for each kind of nanoparticle, we can have like a kind of a signature by looking, for example, how much of the light that is inside in the system is detected. No, after you go through a sample of nanoparticles with the same shape in the system. Another shapes that are possible to do are, for example, these. This kind of decahedral nanoparticles, marks the decahedral, regular decahedral, rounded decahedral. But also you can, for example, find this kind of star nanoparticles or piñata nanoparticles, where we can have a lot of different resonances that give rise to this wide window or wide range of frequencies where the resonances are. So, for example, okay, depending of the shape of the nanoparticle, we can have 6 phases, and we can find, for example, in this case for the cube, we can find 6 different surface plasma resonances. For the truncated cube, now we can see only 4 resonances, and so on. No, and for example, for the star, we can have a lot of resonances that it's quite difficult to identify in this case. Like I said, for example, when the particle is very small as compared with the wavelength of the incident light, what we have is that the response of the nanoparticle, the extinction efficiency of the nanoparticles that the detectors will obtain depends of the dipolar polarizability of the nanoparticle. Okay, and this dipolar polarizability for a sphere, just for a sphere, depends of the sphere radius. Okay, the radius of the sphere, and also for this expression of the polarizability that has to do with the dielectric function of the nanoparticle and where the nanoparticle is. The way that we can match the external field as compared with the column field, column force, for example, and we have these resonances, is when, for example, the dipolar polarizability, the denominator is equal to 0. Okay, so in this way we can find, for example, the resonant or the frequency, the resonant frequency of this nanoparticle, and it depends as I said, of the system or the medium where the nanoparticle is immersed in this way. Okay. As I told you, when we have a silver cube or a nanoparticle which is done by silver, and we have a nanocube of 5 nanometers, in this case, immersed in water, we can find that 6 different modes. In this case, we have identified 1, 2, 3, 4, 5, 6, and where the charges are arranged completely different in all these modes. Okay, and now, for example, you can see that the column forces are quite different as compared with the spherical one. Okay, and for each kind of these arrangements of the charges in the nanoparticles, you will have this resonance where the external force, no, with the column force, given that charge arrangement, are equal, and then you will have this kind of resonances. It is very interesting that, for example, we can identify these resonances, these peaks in the spectrum as a function of the wavelength, and also we can look at this near field or near electromagnetic field in each one of these resonances. And if you can see, for example, for the mode 1, we can enhance up to 3 times, okay, 3 orders of magnitude. We can enhance the near field electromagnetic field, and it has this distribution along the for example, the cube in this case. However, for example, you can see that this peak that is just a small shoulder here, that which is labeled with number 3. Okay, here, just here, we can see this distribution. It is more concentrated in the corner of the cube. Okay, and in this case, for example, we have increased the electromagnetic field up to 6 orders of magnitude. That means that, for example, we are in some way, we are concentrated all the light that comes from the external field, okay, from the electromagnetic wave that inside in the system, and we are concentrated at this particular frequency at a given point in the nanoparticle. Okay, to this kind of near electromagnetic field, it's called the hot spots. Okay, and we can increase up to 6 orders of magnitude the intensity of the electromagnetic field in this way. So this is very nice because, for example, it has been proposed to use this kind of nanoparticles, these plasmonic nanoparticles, like silver or gold, which are the most common, to use to capture the energy from light from the sun, for example. And as I told you, this kind of systems that has these shapes, you know, like these stars or this kind of shapes with some small angles, okay, can cover a large window of energies or wavelengths, no, like you want to see, and also we can increase up to several orders of magnitude as a function, for example, of the angle. Here, for example, if we take into account how much of the energy is increased in a given wavelength because of the response, let me just come back here. We can see that for gold and silver, this is gold, different medium like vacuum or water, another kind of media. Okay, we can have this increment, which is given by these points are where the larger increments are found, and in this way we can not only cover one frequency, but we can cover a large window or large energy window, and then to be more efficient in this kind of plasmonics solar cells, for example. Okay. Another kind of nanoparticles that we can think is, and to look at these shape effects are gold nanorods. It is very common that people can have this kind of decahedral nanoparticles, and then they, by using some chemistry, I'm not a chemist, so I don't know exactly, but they can have that one of these phases, let's say this one in the front, can increase in size, so the people can grow some nanorods in this system. The most typical nanorods and shapes for the nanorods are, for example, the hexagonal, the pentagonal, the square, and the prolate. And here we have also this kind of symmetry of the nanoparticle, but also we have another important ingredient, which is the width as compared with the length of the nanoparticle. And when we look at this kind of systems and we look at the energy equilibrium to grow this kind of nanoparticle, we look that for small nanoparticles, which are equivalent, for example, to a volume of a sphere of 10 nanometers, and as a function of the temperature and the aspect ratio, that means the length as compared with the width of the nanoparticle, as I said, we can have that for small aspect ratios, we have the hexagonal nanoparticle, then we have pentagonal nanoparticle when we increase the temperature, and finally we can have this square and some kind of prolate that where the shape is loose because of the heating, no? Because of the heat up of the temperature. When we have the same, we can look at the same more or less for nanoparticles with a volume equivalent to a nanosphere of 40 nanometers. And we have also this kind of shapes, but the distribution as a function of temperature will change. Mostly we will have, for example, for most aspect ratios and room temperature, we will have almost all the time hexagonal kind of gold nanorods. Now, if we look, for example, a sample, when you have a given number of uniform nanoparticles, these hexagonal nanoparticles or pentagonal nanoparticles and so on, in a solution like water or toluene or something like that, what we look is that the color that you will see at the end, no, when you have transmitted the light, the light that you will see at the end will be the same, independently of the shape or the volume of the particle. What we depend is just of the aspect ratio. That means the length as compared with the width of the nanoparticle. And you can look at these examples also experimentally. And that means that the important features here is that when you, for example, polarize along the nanoparticle, you will have a larger length as compared if you polarize the light along the width of the nanoparticle. And these two modes are the ones that are ruling the optical response of the plasmonic system. And well, you can see exactly the same colors, like the pink, the blue, the red, and then like a dirty kind of solution, no, something like that, a brown like system. Okay. Now what happens if you have the nanoparticle in different host media? I said, for example, we can think that we are in vacuum or we are in water or something like that. And remember that depending on the host where the particle is, you can have that the charges are screened by the media. Do you remember that? No, I guess. So, for example, in vacuum, it means that probably you will have a larger amount of charges in the surface than in water. Okay, and now you will modify the let's say the external force because of this screening of due to the dielectric environment in the system. Okay, so you will have a different force in this case. And now when you have, for example, the silver nanocube in vacuum as compared with water, you still have the same number of resonances, because that depends on the shape of the nanoparticle. Okay, but now the forces that you need to have this resonance and to have this competition between the Coulomb forces, which are almost the same, but let's say less strong because of the presence of the dielectric environment. Now you will have that these peaks are moved to smaller frequencies or larger wavelengths. Okay, so this is what happens when you have a different dielectric environment, and the solution will change in this transmission of light. In the solution will change from, let's say, from this color for this kind of shapes in the silver nanoparticles to this other color if the nanoparticle is immersed in, let's say, in sapphire in that way. Now, what we have done is to try to separate this kind of contributions for the response of the nanoparticle. One is, as I said, the shape of the nanoparticle, and the other important contribution is where the nanoparticle is one, and the second one is the material that compose the nanoparticle. So we have developed a kind of a spectral representation, we call that, where we separate the contributions of both, and we try to understand if we can use this spectral representation to have, for example, this kind of systems where now the people can grow inside of a cube, a spherical particle. Okay, this is a real image of a microscope made by a microscope. So these are real images of real nanoparticles. And now let's say that we have one resonance because of the sphere has one resonance versus 6 resonances because of the cube that has these 6 resonances. And now we can use, using this concept of the spectral representation, we can arrive by a theory that we developed, and in this paper that is here, we can separate these contributions from the matter, let's say the dielectric functions and the geometry, and we can have how much of these modes are coupling with external field. Okay, and at the end we can finish with an effective response of the nanoparticle, and we can compare with experiments. Okay, so now you can, in some way, you can design the response of these nanoparticles, comparing with experiments and so other kind of methods in the system. Now, as I told you, another important thing is how the nanoparticles interact. And let's think that you have 2 spherical nanoparticles. and you have an external field. As I said, well, you have a kind of dipolar distribution of the surface of the surface charges, and this is the electric field, that you can find for each one of these. However, when you have the particles very close to each other, okay, now what happens is that the electric field induced by this dipole also interacts and contributes to the polarization of the second particle, and the same for the second particle. The electric field that is induced will contribute to the second one. That means that now you don't have this anymore, this dielectric field, dielectric light field contribution. Now you have an homogeneous and a high multipolar contribution here, and we can now to look at the different interactions. This will modify, for example, the number of modes, just because of the presence of a second nanoparticle, and also will modify the external fields and the Coulomb interactions that are present on the response of the system. So now we will have not only the dipolar contribution, which is moved just because you have a dimer of this. Not only this single nanosphere is moved to here, but also quadrupolar mode appears in these spheres, and octupolar and another higher multipolar contributions are here. And well, we can look at how much the distance and the array of the nanoparticles are contributing to this response just by looking at different kind of disorder, let's say along a change of made of these nanoparticles. So we can have this kind of modes now. Instead of having a single response, we can have different peaks just because we are changing the distance of two spherical nanoparticles. Okay, and also we are modifying the external electromagnetic field, the near field contribution. So we can modify in this way the response for the dipole just by changing the separation between nanoparticles. And also we can have these different kind of contributions that comes from the quadrupolar contribution that are excited because of the presence of the second nanoparticle, or an octupolar one, okay, and so on. Okay, let me just go to another one. And one important thing is, for example, when we, if you remember, the radiative heat transfer or the black body radiation, this is a kind of a propagating mode. As I said at the beginning, we have a near field, but when we look at, for example, the sun radiation, it is a kind of radiative transfer that is a far field, instead of a near field radiation. And however, when you have a system which is one temperature, let's say the sun and the earth, at temperature 2, for example, and now if you have these two particles which are very, very close, each one, and now also these evanescent modes, not only the propagation or propagating modes, are important. And for very small distances, what happens is that we can increase, okay, the radiative heat transfer by order of magnitudes again, but just at a given frequencies and so on. So what we can do, and we can study here, is how this heat or radiative heat transfer will change, and we can modulate in some way when we have, for example, two nanoparticles at different temperature. And now remember that you have the interaction also with high multipolar contributions and the dipolar and so on. And for different distances, we can modify how much of the radiative heat transfer from this one, which is a higher temperature than this one, for example, than the blue one, is from one particle to the another one. What is interesting is, for example, that we can identify where we can increase this radiative heat transfer, but also we can also control or modify, for example, this heat transfer by looking at a third nanoparticle, and we can increase, for example, the window, where the energy window, just by immersing in between these two nanoparticles a third one. So we can control the heat transfer, okay, the energy transfer in some way, by having different arrays of the nanoparticles in this way. If we have two, or if we have three, we can increase the windows, the energy windows, and the amount of generalized flow of the heat transfer in the system. Another important thing that we can do is, for example, we can have this kind of arrays. These are actual arrays with an hexagonal composition of nanoparticles. We can look that we can couple the plasmonic response of the system between nanoparticles, and now we can have like a propagating mode. These are the measurements of the experimental measurements of these modes, and we can look at different kind of contributions. Here, if you have a constant, this is not a propagating mode. This is the angle as respect to the plane of the system that we are looking for. And also we can have these kind of modes that are propagating. And these modes you can see here for a given frequency, that the near field, okay, is enhanced along one direction or another one, okay? Why we are interested in this is because we can use this kind of substrate of plasmonic arrays, where we can tune the response, and we can increase for a given energies or wavelengths the response of the nanoparticle, and we can couple, for example, with some nanoparticles, okay, some quantum dots. And what is interesting here is that you can have a kind of a quantum dot that has a response, a photoluminescence response. And this photoluminescence is actually in all the directions. However, when you have the array and you have the nanoparticle, we can control the direction where the photoluminescence is going. Okay, so we can have here for a square array, we can have a photoluminescence that has also a square kind of a response. And for this kind of triangular array, we can have this kind of response. And also we can increase in some way, like for example, here we are increasing about 1 order of magnitude the photoluminescence of these quantum dots. So this is a way to control the direction where the photoluminescence of the nanoparticle goes. as well as the intensity of these systems. Okay. Also, what we can do is by looking at these nanoparticles, you can see that these nanoparticles have an array, which is a triangular array, and it's very uniform. However, the shape of the nanoparticle is not symmetric. That means that you have a truncated cone, so the base of this nanoparticle is wider than the top of this nanoparticle, and there is a kind of asymmetry that gives rise again to a kind of a quadrupolar response of the nanoparticle. So you can have a dipolar response, but also you can have a quadrupolar response of the nanoparticle. And if you look at the kind of near field, it's actually exciting. What we have found is that we can look at these resonances, which is the dipolar and the quadrupolar one here. And what we have found is that with the quadrupolar one, we can increase what is called the optical chirality factor. That means we are broken the symmetry of the near field in the system that by using two-dimensional plasmonic arrays, and now we can increase the asymmetry of the near field in the system, and these kind of electromagnetic fields can be used to test molecules which are also chiral and have a response by looking at the circular dichroism of the system. That means that you have a nanoparticle which mirror is the same but in the different sign, okay? And that means that you have this kind of asymmetry. And these molecules are very important because we are made of these kind of molecules like the amino acids. We produce sugars, which are also chiral, and so on. So if you want to test this kind of particles, this kind of molecules, you can use this kind of nanoparticle arrays where you can increase the optical chirality factor and you can increase the response of the system in some way. Okay, I will just briefly to look at this. Now we can do these hexagonal arrays as I showed you. And if you look at the modes that in this honeycomb plasmonic lattices you can find, you can see that you have an analogous of graphene and these kind of materials with the linear dispersion of the plasmonic bands. You can look at and you can modulate the response of this plasmonic response of the system by using polarized light. Like, let's say you have the in-plane polarized light or the out-of-plane polarized light, and you can induce different kind of bands of the system. That means that you can modulate, let's say, the energy of the plasmonic response of the system. And now you can have also this kind of two kind of honeycomb plasmonic lattices. You know, one is you can have this stacking by layer of honeycomb plasmonic lattices. And also, like in graphene, you can have this kind of forbidden or avoided crossing of the bands here. And you can, in some way, to control by looking again into the in-plane and out-of-plane modes of the nanoparticles. Well, as I show you, well, I let's say as a conclusions, I show you that the surface plasma resonance are proper modes that depend on the geometrical parameters, and the shape, the distance of the nanoparticles, the presence of another nanoparticles, and the electromagnetic interaction between nanoparticles and substrate can be represented like by high multipolar surface plasma resonances. And each proper modes couple different with the external field. Okay, and the external field properties can actually couple with different modes. That depends on the external field components. That means if you are looking at polarization along one direction or the other one, so we can tune in some way the frequencies, and we can select the materials, and we can select the arrays, and we can do a lot of things. And this can control the radiative heat transfer. It can control the photoluminescence of quantum dots, and also it can control the chiroptical effects or chiroptical fields in order to test chiral molecules and so on. So this some of the people that works in the Physics Institute, some students, some that have contributed in at some moments to this kind of work. And well, let me finish with this, and also let me thank you for the invitation again to participate today in this talk. Thank you very much.
Thank you very much for your presentation. It was very interesting how the properties change of these nanoparticles with different variables. If is there any questions, feel free of active your microphone. Cesar Martinez, you can open your mic and ask directly to the Dr. Noguez.
Okay. Yes, I'm seeing here two questions. Okay. One is how the different shapes of particles are obtained. Is it by lithography, or what kind of technique is used? Well, there are different kind of techniques. For example, for these two-dimensional systems, mostly are lithography. Okay, or nanolithography. Some of the samples are made in the Czech Republic, for example, for the very small and more sophisticated ones. But also the people can do very simple lithography methods, like to have a substrate, to have a spheres, then to have a uniform film of gold or silver or this kind of materials, and then to take out these nanoparticles, and then you have the holes, and you have this kind of arrange. Also, some other results are the people have obtained by using colloidal methods, no? To synthesize this kind of nanoparticles, and there the people now can control the shape of to have a kind of uniform shape of the system. By we can by controlling the temperature and some external parameters, the people can grow different kind of system. There is another question by Cesar Martinez, that what would be the impact on energy emission transmission if there is a dome on the top of the truncated cylinders instead of a flat surface? Well, you will change for sure the resonances, and you will change the position where the propagating modes or plasmonic modes can couple, and for sure you will have another energy. if you have a more rounded nanoparticle, that depends. For example, how much is the dome? Like how much long is the dome as compared with the width? If you will have this kind of elongated shapes again, or you can have this kind of, for example, let's say, so you can move to different energies. That depends on how is the real shape of the nanoparticle that you are growing up in this way.
Thank you very much. I have a question. Why is important to control the direction of the photoluminescence emission?
Well, for example, in these modern lights and these kind of things, you want to have for some applications, you want to have a control of where the emission is going in this system. For example, you don't want to light all the room, but only one in one direction, like in a laser or whatever. You can have this kind of emission and this kind of control. No? And actually, what it is more interesting is that with this kind of a system, the people is looking at a single photon emission in some way. This is probably the most interesting thing that you can do with this kind of system.
Thank you. Thank you very much. Do we have another question?
Yes, I would like to ask a question. First of all, thank you for your talk. I think it was an amazing talk. And I was thinking about, so I used to teach material science engineering students, and I was thinking about the real applications, right? So I would like to ask, are there any industrial applications for plasmons?
Yes, there are. Probably the most known is that when you have these particles and you can have this increment in the near field, what the people is doing really is heating up the nanoparticles. Okay, so you can in some way to burn some things, by just because you are, let's say, concentrated outline in one place, and there is a practical application. There are now some solar cells that have some plasmonic particles and these kind of things. This is where the plasmonics are present in some sense.
Okay, thank you.
Thank you. We have a question in YouTube. Is there another metal that you have studied, and what was the difference?
Yes, yes, there are a lot of metals. For example, copper is another one, but copper has not a very sharp resonance as compared with silver. And as I said, it depends on the material or the metal where the resonance is. And there are also aluminum, where the resonance is more in the ultraviolet, or in that energy region instead of the red or the green. So what this kind of studies can tell you is that if you want to have the response in a given wavelength or frequency, you can choose the shape and you can choose the material or that you can have. Now, another metals have not this very well defined peaks, in the sense that are wider in some way, because are losing some energy when you inside the light, but the same results can find, and you can look at different materials in the system.
Thank you
This
very
kind of
much.
system.
Is there another question? Feel free to open your microphone. No? Okay. Thank you very much for your time and your presentation. It was very interesting for us. We will continue with the program of this conference. See you to the others for the national evening in Gathertown. And thank you very much, Dr. Cecilia Noguez, for bring us your time and your knowledge.
Thank you to you for the invitation and for this successful Congress.
Thank you very much.
Thank you.
Thank you.
Thank you.